You're listening to the Sonata in A major for violin and piano by César Franck. This movement is structured as a canon, which means that whatever the piano plays is echoed by the violin a few seconds later. It's as if the violin is on tape delay. This music has always reminded me of one of the random processes that we will study in this video, the random phase process. Stay tuned until the end of this video to see why. Now, in the previous video, we introduced the idea of a random process. Each realization of the random process gives us an entire function of time. There are infinitely many random variables, one at each time t. The idea of studying infinitely many random variables at once might seem daunting, but I hope that this first example convinces you that it's not so bad. This first process is called the random amplitude process. We start by defining a random variable a to have an exponential distribution with lambda equal to 0.6. We then define the random process xt to be a times cosine of 2 pi t. Now, in this definition of the random process, there's only one random quantity, that's a. But there are infinitely many random variables here, because you can plug in any value for t and get a different random variable. What makes this random process manageable, despite the fact that there are infinitely many random variables, is that these xt aren't just completely independent random variables. In fact, they're highly related to each other, because the only thing that's random is the amplitude of this cosine. Let's plot a few realizations of this process. If we generate a and it happens to be 0.4, then the function of time is 0.4 cosine 2 pi t, which looks like this. On the other hand, if we generate a from this exponential distribution and it happens to be 1.8, then we get a cosine with an amplitude of 1.8. It's also possible that a is, say, 0.9, in which case we would get this cosine. Now let's zoom in on a particular time t. Let's zoom in at time 2.4. The value of this process at time 2.4 is a random variable. What is its distribution? Well, as we vary a over all the possible values of this exponential distribution, in other words, from 0 to infinity, the random process at time 2.4 can take on any negative real number. So this is a continuous random variable with a PDF, which happens to look like this. Again, the graph of the PDF has been oriented sideways to match the graph of the random process. So we see that positive values of x are impossible at time 2.4, and all negative values are theoretically possible, but values close to 0 are the most likely. Now, how did I figure out that this was the PDF of this random variable? Well, I looked at the definition of my random process, and I simply plugged in t equals 2.4 into the expression. So cosine 2 pi times 2.4 is just negative 0.81. So the random process at time 2.4 is just negative 0.81 times an exponential random variable with lambda equal to 0.6. You showed on an exercise set that if you multiply an exponential random variable by a positive constant, you get another exponential random variable with a different rate parameter, with a different lambda. This negative sign just turns the exponential random variable from always positive to always negative. In other words, it flips the exponential PDF over the y-axis. Now, you might also be interested in the expected value of x at 2.4. To calculate the expected value, you don't even need this PDF. You can just use properties of expected value. The expected value is just negative 0.81 times the expected value of this exponential random variable, which is 1 over lambda. Now, this random amplitude process is quite different from the Bernoulli process we studied in the previous video. First, it is defined for all times t, not just at integer times. So, it is a continuous time process, which, following the tradition for a continuous time signal, we can also notate as x of t with parentheses. Furthermore, at each time t0, x of t0 is a continuous random variable with a PDF. So this process is also continuous valued. A related process is the random phase process. This one is like the random amplitude process, except now the phase of the sinusoid is random instead of the amplitude. We'll assume that the phase is uniformly distributed between 0 and 2 pi. Let's look at a few realizations of this random process. If we generate theta from this uniform distribution and it happens to be equal to 1.26, then our random signal is cosine of 2 pi t plus 1.26, and that function looks like this. Notice that this is a phase-shifted cosine because at time 0, it's not equal to 1. On the other hand, if you generate theta and it happens to be 4.40, you get this random signal instead in orange. And if theta happens to be 5.65, you instead get this signal in blue here. Again, we can look at this process at a specific time, say t equals 3.3. Now, as theta ranges over all the possible values of this uniform distribution, we'll end up getting all possible values between -1 and 1. So this is again a continuous random variable with a PDF, which looks like this. Again, the PDF has been oriented sideways, and you can see that only values between -1 and 1 have non-zero density. And this is actually one of those PDFs that approach infinity as you approach -1 or +1. But the total area under this PDF is still 1. You should think about why it makes sense that most of the area under this PDF is near -1 or +1, considering the shape of the cosine function. Now, how did I figure out that this was the PDF for this random variable? Well, I simply plugged in 3.3 for t in the definition of this random process. And I found that this random variable is equal to cosine of theta, my uniform random variable, plus a constant 6.6 pi. This is a transformation of a random variable whose distribution I know. So I can find the PDF of this random variable by first finding its CDF and then taking the derivative. Now, like the random amplitude process, this random phase process is also an example of a continuous time process because it is defined for all times t, as well as a continuous valued process because if I look at any particular time, I get a continuous random variable. Now, have another listen to Franck's Sonata for Violin and Piano and think about how the violin part is just a phase shift of the piano part.